Good evening to all. I am Dr. Dhondiba, Assistant Professor of Chemistry, Government First Grade College, KR from Bangalore. Today I am going to discuss about fifth session of Chemical Kinetics, which belongs to third semester BSc, affiliated to Bangalore North University. In this session, I have to discuss about Arrhenius equation for energy of activation and solving some problems on it. Now, main objectives of these sessions are derivation of RNA's equation for energy of activation. Second one is activation energy and threshold energy. Energy profile diagram you have to plot and you have to know and solve some problems on this activation energy. These are the main objectives of this session. Now come to that is outcomes of this session. After completion of this, after knowing or after completion of this session, you come to know about what is mean by activation energy, how to plot that is the energy profile diagram, and what the reactant and product indicate in that diagram. That can be explained easily. You have known activation energy and threshold energy, how it is related, that also you can be known, and you can skillfully solve the problems. These are the outcomes of this session. Now, before going to discuss this topic, you have already known about rate constant. What is mean by rate constant, temperature coefficient, and some mathematical skills, plotting the graphs, calculation, subtraction, multiplication, logarithmic properties. These skills you have already adopted before studying this session as a prerequisites. Now coming to that is the actual that is a portion, that is Arrhenius equation. The temperature dependence of the rate of the chemical reaction can be accurately explained by using a Arrhenius, and he given that K is equal to A into e to the power of EA divided by RT, where EA is nothing but activation energy. EA is nothing but activation energy, R is nothing but real gas constant, T is nothing but temperature in Kelvin, and A is nothing but frequency factor, and K is nothing but a rate constant of a particular reaction. This equation is given by using a RNS, and this equation is called as a RNS equation for energy of activation. Same in RNS equation, no, the factor e to the power of EA divided by RT corresponding to fraction of molecules that having a kinetic energy greater than, that is a activation energy. This indicate as the kinetic the corresponding this fraction of the molecule having a kinetic energy greater than, that is activation energy, then only product will be a form. Now taking the logarithm on natural logarithm on both side to equation number 1, then what you get, ln of k is equal to ln of EA to the power of minus A divided by RT. Again by logarithmic property, ln k is equal to ln A plus ln of E to the power of minus A divided by RT. Again by taking the logarithmic property, ln k is equal to ln of A plus minus of EA divided by RT ln E. Again ln E is nothing but 1. Okay. Therefore, this equation becomes a ln of k equal to ln of A minus EA divided by RT, call equation number 2. Plot this ln k against, plot a graph by taking ln k on y-axis and 1 by t on x-axis, which gives that is a straight line according to this equation. Now here this is the equation ln k, it is taken on y-axis, 1 by t is taken on x-axis. You will get that is a decreasing slope. This is a straight line curve with the decreasing. Okay. Now it is the intercept on that is a y-axis. This gives that is a ln of A, and slope of this curve can be find determined by plotting a right angle triangle on that straight line. it will be a theta here, and it becomes a opposite and adjacent, no, therefore slope is nothing but tan theta. It is also called as tan theta, or dy by dx means AB divided by BC, change in y value divided by change in x value. Therefore this is equal to, we will get there is a EA minus A by RT, minus A by RT. If K1 and K2 are the two rate constant at temperature T1 and T2 respectively, then equation 2 can be modified. Equation 2 becomes other two equations. For K1 T1, the ln of K1 equal to ln of A minus EA divided by RT1, call equation number 3. Similarly, ln of K2 equal to ln of A minus EA divided by RT2, call equation number 4. Now subtract equation 3 from equation 4, then we will get that is the ln of K2 minus ln of K1 equal to the second equation, that is the equation 4, equation 4th, no, that is ln of A minus EA divided by RT2 minus of ln of A minus EA divided by RT1. Therefore this can be written as ln of K2 divided by K1 equal to then here ln of A, and this is the plus ln of A minus ln of A get cancelled, and here minus EA RT2 it is remain, and that's minus minus plus, it became a EA divided by RT1. Therefore EA divided by RT1 it is a plus value, therefore you write that is first one. Therefore EA divided by RT1 minus EA divided by RT2. Then take that is a common factor, EA by R is the common factor in this equation. Therefore we can write ln of K2 divided by K1 equal to EA divided by R into 1 divided by T1 minus 1 divided by T2. Then we can take that is LCM of this T1 T2. Therefore ln of K2 divided by K1 equal to EA divided by R into K2 minus T2 minus T1 divided by T1 into T2. Then you have to convert that is a natural logarithm into common logarithm by multiplying 2.203. Therefore 2.303 log of K2 divided by K1 equal to EA divided by R into T2 minus T1 divided by T1 T2. Or this can be also can be transfer, that is a 2.303 that side, what you get. Therefore log of K2 divided by K1 equal to EA divided by 2.303 R into K2 minus T2 minus T1 divided by T1 T2. Or this can be also written as EA is equal to, transfer these all that side, we will get that is a EA is equal to energy of activation is equal to 2.303 R into T1 T2 divided by T2 minus T1, close the bracket, and log of K2 by K1. And this equation is called as the integrated Arrhenius equation. By knowing the rate constant at two different temperatures, the energy of activation can be easily calculated. Arrhenius developed a simple and primarily qualitative theory for the molecular behavior that leads to the above expression for the rate constant. According to Arrhenius concept, reactants do not pass directly into the product, but it first acquires sufficient energy to form a higher energy species that is called as activated complex, which is later break down to form that is a product. Therefore Arrhenius explained that is it is first one is acquire sufficient energy, and it got that is a higher energy, and that higher energy later break down and to form that is a product. Therefore reactant cannot be directly converted into product, but it form a intermediate product, that is activated complex, that will be given by Arrhenius. Here if in the figure X is nothing but here X, actually here it is not visible here. X is the energy of the reactant. X is the energy of the reactant. Z be the that of the product. Here Z is the product, and Y is nothing but that is activated state here. Activated state here. Then the reactant molecule first proceed X to Y. X to Y. It is coming to that side, and here this energy, no, this energy is called as activation energy. The minimum energy acquired of the molecule to get the product, to get the before it crosses the barrier, that is called as activation energy. Therefore it climbs the energy barrier and to roll down the to form that is a product. Here Ex Ex is nothing but energy of that is the normal molecules here, and this is the xy, no, this is the this value is nothing but energy of activation, and this y and z, the difference between y and z, no, this is nothing but energy of threshold energy. Threshold energy, this can be known. Now here the energy of activation is defined as the excess energy which is excess energy which the reactants molecules must acquire in order to take part in the reaction. The excess energy acquired the molecules to take the part in the reaction, or it may be interpreted as energy to form that is activated complex. The idea of the activated complex can be represented as a plot of energy of the system versus that is a reaction coordinate. The reaction coordinate doesn't corresponding to any single intermolecular distance, but rather depends on all the intermolecular distances that changes either reactant molecules into product. Therefore we say that is a here sufficient energy required to cross the barrier, that is called as a activation energy. And activation energy, sum of the activation energy and normal energy possesses the molecule, that is called as a threshold energy. Threshold energy. And coming to that is limitations of Arrhenius theory of energy of activation. This theory fails to explain that is Arrhenius frequency factor. This theory, it is fails to explain that is Arrhenius frequency factor. This is about that is Arrhenius theory. Now we have to solving some problems on this activation energy. First problem goes to, for a reaction, the values of the rate constant at 298 Kelvin and 238 Kelvin were 3.46 into 10 raised to minus 5 and 4.81 into 10 raised to minus 3 respectively. Calculate the energy of activation. The given that R is equal to 8.314 joules per Kelvin per mole. Solution for this, given that K1 is equal to 3.46 into 10 raised to minus 5, K2 is 4.81 into 10 raised to minus 3, T1 is nothing but 298 Kelvin, T2 is nothing but 338 Kelvin, R is nothing but 8.314 joules per Kelvin per mole. Then calculate the energy of activation. Activation energy is equal to what? Now you know that the calculation or expression for energy of activation is equal to EA is equal to 2.303 R into T1 into T2 divided by T2 minus T1 into log of K2 divided by K1. Now substitute the value of that is 2.303 into 8.314 joules per Kelvin per mole into 298 into 338 divided by 338 minus 298. Therefore log of, we will get that is K2 is nothing but 4.81 into 10 raised to minus 3 divided by 3.46 into 10 raised to minus 5. Then you have to subtracting, you will get that is after multiplication we will get 19.147 joules per Kelvin per mole into this is the keeping as it is 298 into 338 divided by 40 log of 139.017. After this is the taking the log, no, log value is nothing but here 2.14, and after multiplication we will get that is 48214.418 into log here nothing but you say that is characteristic of logarithm is 2 and 13 under 9 you have to see, you will get that is a 1400. Therefore 2.1400 is the logarithm, and then after multiplication we will get that is a 103,178.85452 joules per Kelvin per mole. The energy of activation usually expressed in terms of that is a kilojoule. Kilojoule means divide and multiply by 1000, and above that is a numerator value you put that is a k and divide this number by 1000, you will get that is a, after dividing 1000 you will get that is three decimal points shifted towards the left side. Therefore we will get that is a 103.1788 kilojoule per Kelvin mole. This is the energy of activation. Now second problem is nothing but calculate the rate constant for a reaction at 700 Kelvin given that rate constant at 6 Kelvin is 3.5 into 10 raised to minus 4 per mole per second. The energy of activation in this temperature range is 140.3 kilojoule per mole. This is the given. Then calculate the rate constant. Now here what are given here? You know that T1 lower temperature is always T1. The given that T1 is nothing but 600 and K1 is nothing but 3.5 into 10 raised to minus 4 per mole per second, and T2 is nothing but 700 Kelvin, and energy of activation in this range means EA is equal to 140.3 kilojoule per mole given. Therefore I have written here K1 is nothing but 3.5 into 10 raised to minus 4 mole per mole per second. K2 is you have to find out rate constant at 700 now, that you have to calculate, and T1 is equal to 600 Kelvin, T2 is nothing but 700 Kelvin, R is nothing but 8.314 joules per Kelvin per mole, EA is nothing but 140.3 kilojoule per mole is given, but this should be a convert into joules per Kelvin. Okay, the kilo means you have to put that is a into 1000. Therefore 140,300 joules per Kelvin per mole. This will be a will get that is the energy of activation. Now we know that from the Arrhenius equation, log of K2 divided by K1 equal to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2. Substitute these values in this equation. Therefore we will get that is log of K2 divided by 3.5 into 10 raised to minus 4 equal to 140,300 divided by 2.303 into 8.314 into 700 minus 600 divided by 600 into 700. After this is subtracting, you will get that is a it is only it is 100 and it is multiply, we get that is a 4 to 4 times 0, and this multiplying after this we will get that is a 19.147, and 1 divided by, after dividing 1 to this number, that is 3.5 into 10 raised to minus 4, we will get that is log of 2857.14 into K2 equal to, after this is the same, divide by this, and here these two get cancelled, these two get cancelled. After simplifying, after multiplying, we will get that is a log of 2857.14 K2 equal to 1403 divided by 804.174. Then you have to transfer to this log, no log value you have to transfer that side. After dividing that you will get that is a log of 2857.14 K2 equal to 1.7446. Then you have to transfer log that side, anti-log it became. Therefore 2857.14 K2 is equal to anti-log of 1.7446. Then you have to see the anti-logarithm 74 under 4 and mean difference 6. After adding you will get that is a 55 54. Then you have to add one number 1 to this number 1, therefore 1 plus 1 2, therefore uh, two decimal two digits will be shifted, the decimal point from left side to two digits will be shifted, therefore 55.54 will be the this anti-logarithm. Then you have to divide, that is k2 is equal to 55.54 divided by 2857.14. You will get that is a k2 is equal to 0.019439. This can be in the form of 10 raised to power. You can write that is a k2 is equal to 1.9439 into 10 raised to minus 2 per mole per second, and this is the k2 value. Now so far we have studied about there is a Arrhenius theory of activation energy, then energy profile diagram we have already learnt. Then activation energy and threshold energy also we have understood. Then we have solved some problems on activation energy and rate constant of that equation. Now I will ask some questions, you have to answer. The Arrhenius equation for activation energy: A option, k is equal to a into e to the power of a divided by 2 RT. B option, k is equal to a into ea divided by RT. C option, k is equal to ea minus ea divided by a into ea divided by RT. And D option is none of these. These are the options are given. You have to answer correct. You have to choose the correct option for this question. I will give that is a 10 second for you people. Answer for this question is C option. C is nothing but k is equal to a into e to the power of a divided by RT minus a divided by RT. This option is nothing but this equation is called as a Arrhenius equation for energy of activation. Therefore, C option is the correct answer. Then second question, which statement is true? Threshold energy is equal to activation energy plus normal energy. Second option is threshold energy is equal to activation energy minus normal energy. Then threshold energy is equal to activation energy divided by normal energy. And fourth one is none of these. I will give that is a 10 seconds for you people. You choose the correct answer for this. The A option is the correct answer for this question, because the threshold energy is nothing but sum of the activation energy plus normal energy. Normal energy molecule possesses the energy possessed by the molecules, that is called as normal energy, and the normal energy plus activation energy, this gives that is a threshold energy. Therefore, the threshold energy is nothing but sum of the activation energy plus normal energy, and the option A is the correct answer for this. This is the true statement, and others are wrong concerned to that is threshold energy. And I have prepared this session by using these books for reference purpose, and thank you.